Great. Hi, I'm Andrew. I'm a PhD student working at Rich Turner, and I'm going to be giving this reading group with David, Burt, and Javier, Antoran, yeah. So I'll do the first part, David will do the second part, and Javier will do the third part. This reading group is an introduction to PAC Bayes. I'll be talking about the PAC framework and introduction to PAC generalization bounds. David will be talking about PAC Bayes specifically. And Javier will be talking about applications of PAC Bayes. During this talk, I won't be assuming that you're familiar with the PAC framework at all. So if you know PAC stuff already, the first part of this talk will be very elementary for you. But if you're not familiar with PAC at all, then this should still be something you can follow, hopefully. So let me start by giving some motivation for why we might be interested in PAC Bayes. There are a lot of different angles you could come at this by. One of them is the desire to explain the phenomenon of generalization in deep learning. With PAC Bayes, you can actually prove that with high probability, stochastic neural networks with millions of weights will generalize. This is something we all know to be true, but coming out with rigorous statements that showed, like, numerically that we are guaranteed to generalize is actually extremely difficult, and PAC Bayes is one of the most promising methods in this direction. So yeah, one motivation is we want to explain generalization. Another motivation is that we might want to actually develop novel learning algorithms based on PAC Bayes. So recent work has suggested modifying, for example, the elbow objective using PAC Bayesian arguments in such a way as to deal with model misspecification. And Javier is going to explore that during his part of the reading group. We might also want to just understand what the relationships are, if any, between Bayesian and frequentist learning. And in fact, PAC Bayes can give a pretty interesting justification on frequentist grounds for performing Bayesian inference without assuming that we have the correct model, which is always in the back of the mind of the Bayesian. Do we have model misspecification or not? PAC Bayes can actually motivate doing Bayesian learning without making that assumption. And yeah, so this talk will have some math derivations in it and some conceptual, perhaps slightly subtle conceptual issues, especially if you've not seen this stuff before. So please ask questions during the talk. Our hope is very much that you can follow the equations. And if you're having trouble following the equations, probably some other people are too. So feel free to stop me and I will happily clarify what's going on. Okay, so just some words about the PAC setup. So before we get to PAC Bayes specifically, what is PAC? What is the PAC framework? PAC stands for probably approximately correct. I'll clarify why it's called that later. And it's a frequentist framework. And here we're going to consider supervised learning, although there are variations of this that deal with other kinds of learning as well, but supervised is the most common. And specifically, we're going to consider classification. Oh, I guess we don't really strongly specialize to this, but think of a classification problem with input space X and output space Y. For example, X in the input domain could be an image, and you could think of Y as a set of labels. So maybe you want to do binary classification, so it's -1 + 1. And you let D be some unknown data generating distribution over X times Y. So think of D as a distribution over natural images plus their labels, for example. Now we're going to define a hypothesis space, curly H, and it's going to be a set of functions from X to Y. So think of H as a set of classifiers. It takes images, and any element of H is a function that takes an image and spits out a label for that image. So for example, a neural network. In the PAC setting, we view the learning algorithm as choosing a hypothesis, or also known as a predictor, which is just an element of H. So what our learning algorithm does is it takes a data set, it does some learning, and then it returns a predictor, which is a function from X to Y. And then, of course, the question is, how do we choose a hypothesis in our hypothesis space? In order to do that, we need to define a loss function. So a loss function is a map that takes an input, an output, and a predictor, and it gives you a real number. So what this loss function does intuitively is it tells you how much loss your hypothesis incurred when it saw data point X and which had label Y. And we're going to define the generalization risk, or also known as the true risk of this hypothesis, as the loss that we incur on the point XY when we use hypothesis H, and we take the average of that loss when you average over data point pairs XY from the true data generating distribution D. And this defines the true risk of H. It's, yeah, so it's just the expected loss under the true data generating distribution. And in your mind, think of the 0-1 loss, for example. So the 0-1 loss is defined as the loss on XY, if you use H, is just 1 if H of X is not equal to Y and 0 otherwise. So 1 is the indicator function. This is just the event of misclassification. And the loss is 1 if you misclassify, and it's 0 if you don't misclassify. And in that case, if you substitute this 1 into this slot here, what you end up with is that R of H is just a probability of making an error when you draw a new sample from the data generating distribution. So this generalization risk is usually a quantity that we're very interested in. And we want to choose H, or a hypothesis, such that the generalization risk, or the true risk, R of H, is minimized. Okay, the immediate problem is we don't know what the true data generating distribution is, D. We don't have like a closed form expression for D. D is like a distribution over ImageNet examples, or the distribution over MNIST examples, for example. We don't know what D is mathematically. So we definitely can't exactly compute R of H. So what do we do instead? Well, we try to compute a proxy. So instead of the true risk, we can consider the empirical risk. And what we do is we estimate the true risk by sampling a data set. A data set is a finite collection of input-output pairs that are sampled IID from D. And think of a data set as the MNIST data set, for example. So imagine D as being the distribution of written digits, and MNIST as being a sample, a random sample from that distribution. And we collect N of these. So in the MNIST case, N is 60,000. And then we're going to use this sample to choose H dependent on the sample, or H sub S. Sometimes I'll suppress S, and I'll hopefully let you know when I do that. And then we use this to compute the empirical risk. So remember previously we had the generalization risk, or the true risk is capital R. Now we come up with a surrogate called the empirical risk, which is little r, and it depends on S. And the empirical risk is just the Monte Carlo estimate, 1 over n, and then you sum over all data points in S of your loss. So really, it's the loss that you observe when you actually train on a neural network on a data set. And notice that it depends on S in 2 ways. It depends on S because it's a Monte Carlo estimate and we use S, but it also depends on S because the hypothesis that we're testing, the hypothesis that we're evaluating the empirical risk on, depends on S. And S is the data set or the sample. Now, what PAC bounds do is that they upper bound the true risk, which is R of H sub S, in terms of this empirical risk. So remember, the true risk is what we're really interested in. You think of it as like the risk in the wild, but we can't actually measure it because we don't know D. What PAC bounds do is they allow us to upper bound the true risk in terms of this empirical risk, which is easy for us to measure because it just depends on the sample data set S. Okay, so now I'm going to insert a warning for Bayesians and just mention some things that I, as a Bayesian, was very confused with when I first encountered this topic. In Bayesian thinking, to be unknown is to be synonymous with being random, and to be known is synonymous with being deterministic. So if I know a quantity, it's not random. If I don't know a quantity, I model it as random. This is not so in the PAC framework, and specifically, it's not so in PAC Bayes. So even though PAC Bayes has the word Bayes in it, it really doesn't have this kind of Bayesian thinking. For example, we know the data set S. So for example, we know what the MNIST data set is, so we know what the ImageNet data set is. But in the PAC setting, S is treated as a random variable sampled from the data generating distribution D. This is very different from the Bayesian way of viewing it. It's still viewed as random according to PAC. Conversely, D is unknown. We don't know what the data generating distribution is. If you were a Bayesian, you might be tempted to place a prior over the parameters of D, or the shape of D, or the form of D, and do some kind of update with Bayes' rule. It would be extremely difficult, but that's sort of what you might try to do. This is completely illegal in the PAC setting and in PAC Bayes. D is unknown, but the form of D or the parameters of D, whatever they are, it's deterministic, and we're not allowed to treat D as a random distribution. It's of course a distribution, but we're not allowed to have a distribution over distributions in the PAC setting. So hence, in this talk, all the randomness is going to be coming from S, even though we know what S is. S is the data set. So for example, the data set is random. If you use the data set to choose your predictor, HS, that's also random. If you compute the empirical risk, that's doubly random. It's random because the empirical risk is random, and it's random because the hypothesis is random. And even if you compute the true risk of your predictor, which depends on S, that's also random because S is random, so your hypothesis is random. So the true risk of the hypothesis is random. They're all random through S. Conversely, D is not random. It's unknown, but it's deterministic, the data generating distribution. And if H is chosen independently of S, so if H is non-random, then the true risk of H is non-random. Okay, so I kind of mentioned a lot of terminology. Does anyone have any questions about what I've said so far? All right, great. I hope that means I was clear then. Okay, so the natural question to ask is, okay, if D is not known, I don't know the data generating distribution, and I can't model it probabilistically, I can't be Bayesian about it, for example, how can I say anything at all? Well, what we're going to do is we're going to seek theorems that hold with high probability for any choice of D, any D at all. So in that sense, PAC bounds constitute a worst case analysis. They tell you what we can say, even if you don't know anything about the data generating distribution, except that we sample IID from it. However, we're doing a worst case analysis, that seems pessimistic, but we get away with very weak assumptions. Typically, we just assume that this IID assumption, and in particular, we don't need to worry about our priors or model mismatch, which is what the Bayesian worries about all the time. Our theorems that we're gonna present in this PAC setting are going to be completely free of assumptions on the data generating distribution, which is very nice. Okay, so let's introduce the simplest PAC bound possible, which is a validation bound. So let's consider the special case where your hypothesis does not depend on the sample S at all. So H is chosen without any reference to the sample. This arises naturally if H is learned using some training data, which we think of as non-random, but we want to bound its error using a validation set. So think of S as sampling a validation set, and we're not allowed to use the validation set for learning. H is learned in some completely different way that we're not going to think about, but we're just going to use S as a validation set. So H is not subscripted with S because it's not, and therefore H is non-random. What we want to do is we want to bound the difference between the true risk and the empirical risk. So the true risk R of H is this expectation, is what we care about. The empirical risk R S of H is the loss on your validation set, and it's what we can actually measure. And we want to bound this difference. Since H in this case, the special case, doesn't depend on S, then the right-hand side here is just an average of IID random variables. So X and Y are random, remember. H is non-random. X and Y are all IID. So therefore, this is just a collection of IID random variables, and we take their mean. And the left-hand side of this term is just the average of the right-hand side. It's deterministic, it's just the mean of it. So what we've got here is the difference between the mean of a random variable and the Monte Carlo estimate of that random variable. And this is something that's well studied. And we can use a concentration inequality to bound deviations of the average, of the empirical average from the true mean. So I'm just going to quote a well-known theorem in concentration inequalities called Hoeffding's inequality. Hoeffding's inequality states that if Z1 to Zn are IID random variables and they're bounded in 0, 1, then for all epsilon positive, or like choose any positive real number, then the probability that the empirical average is more than epsilon away from the true average is upper bounded by twice it's upper bounded by a term that's exponentially small in n and epsilon squared. So think about it this way. If the probability of a deviation greater than epsilon goes down as epsilon goes up, because then this exponential term is smaller, and as n goes up. So obviously, if you have more data points, then your probability of deviation goes down. And if you want to consider large deviations, then the probability of that deviation goes down. So if we rearrange this by writing delta equals the right-hand side term, then you get with probability at least 1 minus delta that the empirical risk minus the empirical average minus the true mean is upper bounded by this term. Now we can just let Zn be the loss on one of the data points, and then Hoeffding's inequality immediately gives that the true risk is upper bounded by the empirical risk plus this term here. And this is just because the true risk is the true mean of the empirical risk, and this is just a Monte-Carlo estimate, so we use it immediately. And you think what you can do is you think of the red term as a gap term. It's a gap which says how loose, I guess, this bound is. So what we do is we compute the empirical risk, and then we add this gap term, and this gives us a probability at least 1 minus delta bound on the true risk. And this gap, it shrinks if you have more data, and it shrinks if you allow a higher probability of failure, delta. This is our first PAC generalization bound. And now I can tell you what PAC means. Probably means with probability 1 minus delta over the sampling of the data set S. That's what probably means here. Approximately means we have a gap term, and this gap term is in red. So it's approximately correct because it might be loose. But of course, this is an artificial setup. This is just validation bounds. We don't really care about validation bounds as the most important application. We want to choose H in such a way that it depends on S now. What can we do? Well, now it's time for another warning. And this time the warning is about interchanging the order of words. Recall that the previous result about validation, it holds for all H with high probability. So think about it this way. For any hypothesis at all, with high probability, this result holds. And high probability means probability 1 minus delta. This is very different from saying that with high probability, the result holds for all H. So interchanging the order of words is dangerous here. Let's think about it this way. So let's consider this a graph, and I'm sorry, this graph has change notation. So let me just try to explain. G is a hypothesis.
Andrew, you have a question in
chat. Oh, sorry, I can't actually see these.
Okay, so Siddharth asked, will this validation bound be the best we can get when not choosing H as a function of S?
No, this is not the tightest possible bound. You can get tighter ones based on a different inequality. So instead of using Hoeffding's inequality, you can use a Chernoff bound, and that gives you a tighter bound, a strictly tighter bound. I'm not sure what's the tightest possible bound, but this isn't the tightest one. It's just a very simple one. Cool. Were there other questions? Are there any other questions? Oh, sorry. I found the chat. Okay, sorry. There's lots of questions. Okay, it's at least a factor of 2 loose. Yeah, it's at least a factor of 2 loose. You can even tighten it beyond that just by using Chernoff bound and by using it like a Bernoulli, using a different concentration inequality. Okay, Andre says, does this mean that in other cases, regression, we need to make sure the loss function is valued between 0. Is there a standard scaling technique? Okay, yeah, that's a good question. So as long as you have a bounded loss, you can always scale the loss and then apply Hoeffding's inequality. And then you just end up with these scale factors all over the place. If you have an unbounded loss, things get trickier. And then you usually need to make some other kind of assumption. There's a paper that called PAC Bayesian theory meets Bayesian inference or something like that from 2015 that considers unbounded losses, but they need to make a sub-Gaussian assumption on some of their random variables. We won't be covering that in this section, in this talk. We'll mainly be considering bounded losses, and then things are usually quite simple for that case. Great. Okay, so I'll move on to this warning about interchanging words. Okay, if you think of the x-axis here as the set of all possible hypotheses, and think of G as an individual hypothesis, and on the y-axis, think of that's the risk, and this line here called R of G, that is the true risk of hypotheses, and R sub n of G. Sorry for the change of notation. R sub n of G is the empirical risk, and think of n as the sample. And what happens is every time you sample a data set, you create a new curve sub R sub n of G. Our result says that if you fix a single hypothesis G, and then you sample a data set S, the empirical risk, R sub n of G, will be close to the true risk. So let's consider a single G, and then you sample many of these curves, R sub n of G, and our result says that with high probability, R sub n of G is going to be very close to R of G. In other words, the empirical risk is going to be close to the true risk. But if you switch the order of the statements and you want to say with high probability for all H, this is true, that's sort of implying that with high probability, the curve R sub n of G is going to be close to the curve R of G over the entire x-axis, which is clearly not the same statement. So, so we have to be careful about switching the order of words. And the latter statement is much more useful. If we have the latter statement, which says that with high probability for all data sets, so for all hypotheses, the empirical risk and the true risk are close, this actually allows us to choose the hypothesis in a way that depends on the data set S and still obtain a high probability guarantee. And this is a very useful statement because it means that we can learn. We can use H, we can use the data set S to choose H. So what we're going to do is we're going to seek a statement that says with high probability for all H, ... For finite hypothesis spaces H, we can use a union bound to do this. And recall a union bound says that the probability of a union of events is upper bounded by the sum of their probabilities. And what we're going to do is we're going to upper bound the probability that our bound fails for any hypothesis at all in the hypothesis class. So let me just walk through this one line at a time. We want the probability that there exists a hypothesis in our hypothesis class such that the generalization bound fails. So it fails when the true risk is greater than this empirical risk plus the gap term. So the probability that it fails for any hypothesis is the probability of a union, and this union is over all the sets, all the data sets S, such that cause the hypothesis to that cause the bound to fail for that hypothesis. Remember, S is a random thing here, and we're taking a union over all hypotheses of this event. Now we can apply the union bound, and it just says that it's upper bounded by the sum of the probabilities, and we sum over all the hypotheses in our hypothesis class, and the union bound is now over the probability that one hypothesis fails. Now, if you think of this, in this statement here, H no longer depends on S because H is just something that we're summing over. We're summing over all the hypotheses, and therefore we can now apply our previous result, which was our validation bound result, which relied on the fact that H doesn't depend on S. And now we know that the probability of failure is at most delta. So now what we've gotten is that the probability that there exists a hypothesis that causes the bound to fail is upper bounded by the size of the hypothesis class times delta. and I'm just repeating this inequality here. And if we choose delta prime to be h delta, and we just relabel things, then we end up with high probability, sorry, with probability at least 1 minus delta prime, for all h simultaneously, the true risk is upper bounded by the empirical risk plus what looks like our old gap term, but now we have a term in red, log of the size of the hypothesis class. So you can think of this as the price you pay for getting a bound that holds simultaneously for all hypotheses in the hypothesis class. So this bound holds even if we pick h dependent on s, because it holds for every hypothesis. So in particular, it must hold for hypotheses that are chosen dependent on s. It's identical to the validation bound, except for this red term, which you can think of as a crude measure of how complex your hypothesis class is. And then now, obviously, the question is, union bound didn't seem very interesting. Can we do something more interesting than union bound and get tighter bounds that way? And the answer is yes. If we use randomized hypotheses, we can use PAC Bayes, and David's going to talk about that. Just quickly before I hand over, does anyone have questions about this setup? Great. All right. In that case, I'll hand over to David, who will talk about PAC Bayes specifically. David,
yeah. Can you see my screen there now?
Yeah.
Great. Okay, so PAC Bayes is going to look a lot like Bayes, but it is frequentist, as Andrew mentioned earlier. So there will be some differences to highlight. So we're going to start by defining a prior, which we'll denote by P, on hypotheses. So this is on the space of possible hypotheses. And this prior shouldn't depend on S. And one thing to just highlight here, and I'll highlight again later, is that P isn't really a Bayesian prior in that it doesn't necessarily have to model our beliefs about the system or anything to do with the data generating process. It's just some distribution that doesn't depend on S. We're also going to define a posterior Q, and Q is allowed to depend on S. So sometimes I'll denote it by Q of S. Most of the time I'll just denote it by Q. But it's important to remember that it does in general depend on S. So it's kind of it's a random distribution in the sense that S is random and Q depends on S. But Q itself is also a distribution. And we're also going to define a kind of new versions of the risk. So one is the true risk, but averaged over hypotheses drawn from Q. So this is kind of like you sample from your posterior and then compute the risk of that sample. And that's maybe slightly different from what you would typically do in the Bayesian setup, where you might try to integrate out the hypothesis and then compute the risk of something like the mean hypothesis. But that's the quantity that we're going to try to bound. And similarly, we have a kind of empirical version of that risk, which is you sample from Q and you compute the empirical risk on the data set S, conditioned on the data set S. PAC Bayes is going to give us bounds of a form that the true risk averaged over Q is upper bounded by this empirical risk averaged over Q, plus some function, which is going to roughly measure the difference between Q and P, and it should probably go to 0 as the number of data points goes to infinity, keeping all else equal. And then it will get bigger if delta gets smaller. And this is going to hold with probability 1 minus delta. for all Q simultaneously. So this is the point Andrew is highlighting later, where Q is now allowed to depend on S because it holds for all measures Q. Okay, so again, we've said this several times at this point, but the assumptions in PAC Bayes are different than those in Bayes. So we need this assumption that data is IID from some unknown distribution, and we don't typically have this in Bayes. We also don't have an assumption that P is related to data generating process or prior beliefs about the data. So P will affect how tight our bound is, but the bound will be valid for any P as long as P is independent of S. Okay, so now I'm going to just state one of the kind of classical results in PAC Bayes, which says that for any loss, which is in 0, 1, for any data generating distribution, for any space of hypotheses, and for any prior P, which is a probability measure supported on this space of hypotheses, and for n greater than 8, we have that the empirical risk is upper bounded. Sorry, the true risk is upper bounded by the empirical risk, plus something which looked very much like when Andrew applied the union bound to Hofstad's inequality. So we have the square root of something over 2n. We have this log 2 delta that Andrew had before. This log root n is new and is just kind of a new constant term. And then we have the KL divergence between Q and P. And this holds for all Q. And again, because it holds for all Q, Q may depend on S, supported on H.
So there's a question.
Yeah, sorry. Yeah,
Dave Jans says, remind me what n was.
Yeah, so n is just the data set size in this case. So it's a number of samples. Yeah, great. Okay. And I'm just going to use this notation less than or equal to with a 1 minus delta over to denote that this inequality holds with probability at least 1 minus delta. So you can minimize this right-hand side with respect to Q as a way of finding the posterior, since this holds for all measures Q. And one thing that kind of highlight for kind of Bayesians is that if you were to choose L to be the log likelihood, which okay, maybe you can't because L is in the set 0, 1, but at least kind of if you were to allow for that, then minimizing this right-hand side would look a lot like variational inference. And Javier is going to get more into this later when he talks about applications, but this would be basically the expected log likelihood. And then you'd have something which looks like a square root of a KL divergence instead of a KL divergence. Also, if the hypothesis space is finite, and we were to choose our prior to be a uniform measure on the space of hypotheses, and Q is a point mass, so Q assigns all its probability to a single hypothesis, then the KL divergence between Q and P would just be the log of the cardinality of the hypothesis space. And so then it would look a lot like the union bound that Andrew presented, except for this kind of pesky log root n factor. Okay, so now I'm going to get into how this bound is actually derived, and please stop me or ask questions kind of as needed. The main challenge is going to be that the bound involves expectations under Q, and Q depends on S in perhaps a complicated way. So that would depend on the details of the learning algorithm. And so we don't really want to take expectations under Q. So the idea is going to be to convert expectations under Q to expectations under a prior P, which since the prior is fixed and independent of S, these are easier to handle. So we're going to just suppose P and Q have densities, P and Q respectively. And then we can, then kind of one of the main lemmas for proving this PAC Bayes result will be the change of measure, which kind of maybe doesn't look super intuitive at first. But before kind of going into what it says, I'll just say that if you were to take phi, which is an arbitrary function, or arbitrary measurable function, to be the log likelihood, and you were to choose P to be a Bayesian prior and Q to be a variational posterior, then this would just be the expected log likelihood under the variational posterior minus the KL divergence between Q and P. Sorry, can you still hear me?
Yes.
Okay, cool. This would be the log marginal likelihood, because e to the log likelihood would just be the likelihood, and you would be integrating under p and then taking a log. This would be the KL divergence between the variational approximation and the true posterior. And this would be, and this is just saying that this is upper bounded by the log marginal likelihood using non-negativity of KL divergence. But in general, we can replace the log likelihood with an arbitrary function phi, and then we get this upper bound in terms of the log of the integral of the exponential of a function under the prior. Okay. So I'll quickly go through a proof of it. If you've seen the proof of Vielbo, it's basically the same proof. So we're just going to expand out this KL divergence from Q to or between Q and this term, which is so the p hat is defined with this density, and this is sometimes called the Gibbs posterior. And if we just expand that out, and just multiplying through by 1, we get the right-hand side, and then using the log of a product is the sum of the logs of the two terms. We get there should be an integral sign here, but we get the KL divergence between Q and P, as well as this other term. And if we look at the second term, then just using the definition of p hat, it's equal to this. And then if you just shuffle terms around, you get the original statement. Okay, so maybe that's so if you didn't follow this, but you know it's a derivation of elbow, this is just the same thing. Okay, we're going to basically need two other inequalities to prove or to go through most of a proof of the Macalister's theorem, which is the PAC Bayes result I showed. And the first is Markov's inequality, which is maybe familiar, which says that if you have a non-negative random variable, and if you fix any real number a, which is non-negative, then the probability x is a times greater than its expected value is less than 1 over a. The second result we'll need is Jensen's inequality, which you've probably seen before, which just says that if you have a convex function f, and these moments are finite, then you can pull then if you pull f outside the expectation, you get a lower bound, and vice versa. Okay, so now I'm going to go through the proof of Macalister's bound. If you have any questions up to now, stop me. Otherwise, I'll keep going. So we're going to define this function delta, which is going to take an empirical risk, a true risk and an empirical risk, and it's going to compute the squared differences between them. And so what we're actually going to bound is we're going to upper bound delta of RQ of and RS of Q with high probability. And that's going to tell us that the true risk is near the empirical risk. So because this is a convex function, we can pull the expectation over Q outside of delta. And that's going to give us an upper bound on delta. So now we have the true risk that Andrew referred to, and the empirical risk that you referred to because Q is on the outside. So again, we have this expectation under Q, and we don't really want expectations under Q. We'd rather have expectations under P. And so we're going to use the change of measure, which is all that I'm bringing up here. And we're going to apply this to the function phi equals 2n times the thing inside this expectation. And then after rearranging, we get that that this thing, which was the upper bound we had on delta in the previous slide, is upper bounded by 1 over 2n times the KL divergence plus the log of this expectation under P. So this is already starting to look like the bound we want. We have this 1 over 2n, which showed up. We have this KL. So the main thing left to do is to upper bound this term and then do some rearranging. We're going to apply Markov's inequality to this because we also have this expectation under Q. And what this is going to tell us is that, we're going to apply Markov's inequality to this, the inside of this term. And that's going to tell us that with probability 1 minus delta, the log of this expectation under P is upper bounded by the log of 1 over delta times its expected value. So this expectation is over hypotheses sampled from P, and this expectation is over data sets drawn from the data generating distribution. Now what we need to do is upper bound the term that showed up inside this log when we applied Markov's inequality. So we're going to interchange the order of integration. And so instead of first integrating over over hypotheses drawn from prior and then over samples, we're going to first integrate over samples and then over hypotheses drawn from a prior. And this becomes kind of nice, even though it doesn't really necessarily look it, because if you look at the random variable n times the empirical risk conditioned on h, this is actually a binomial random variable. You can think of our S of h, since our loss took values in 0, 1, our S of h can take values in 0, n. Maybe this should be divided by n. I'm looking at this. No, it should be times n. Yeah, so our S can take values in between 0 and 1. And it can take on the values 0, 1 over n, 2 over n, so on. So n times it can take on the values 0 through n. And the probability that any of these coin tosses is heads is equal to the empirical, the true risk of the particular hypothesis sampled from P. Does that make sense? If not, please ask a question. Okay, chat. Okay, yeah. So right now the loss takes values in the set 0, 1. There is a generalization of this, which is not much harder to show, which allows for the loss to be in the set from 0 to the interval 0, 1. Mm-hmm. And then this, what ends up being an equality here will have to be replaced by an inequality, and you'll have to use Jensen's inequality one extra time. So right now I'm assuming it's in the set 0, 1, but it's not hard to generalize.
Okay, I would have assumed the other one would have a tighter bound, but maybe not. I'll just thanks.
Yeah. Okay. Yeah, so using that this is binomial, we can rewrite this as a sum over possible values that the empirical risk could have taken. So it's k from 0 to n times the binomial probability mass function with parameter r, with the parameter equal to the true risk, times the function that was inside the exponent. And this true risk is unknown. So we want to get rid of that in the bound so that we can actually compute the bound. And so we do that by replacing this expectation with a soup over possible values of the true risk. So now, basically what's left to do is to upper bound this soup and then do some rearranging on the initial bound. Okay, I'm not actually going to upper bound the soup. So sometimes this is quite involved, and kind of there's a lot of similar PAC Bayes bounds, and they kind of need different techniques to upper bound this soup, so it's maybe less important in terms of understanding how PAC Bayes works. But using Stirling's formula, as well as Pinsker's inequality, you can show that this upper bound that this soup over this sum is upper bounded by 2 root n. And so then if you were to just plug that in to what we had a couple slides ago, you get that the squared difference between the empirical risk and the true risk is upper bounded with probability 1 minus delta by the KL divergence plus this log term in 2 over n. And then if you just take a square root and move the risk to the other side, you get the initial bound that was stated. Okay, so that's basically the proof up to this upper bound, which is a bit technical, but not necessarily the most interesting bit of it. So kind of just wrapping up, there's also a bunch of other PAC Bayes bounds with similar proofs. So sometimes these bounds look kind of scary, but it's good to remember that at least a lot of the kind of more classic ones basically just use Jensen's inequality and Markov's inequality, and maybe something like Hofting's inequality, or some other concentration inequality, but the kind of inequalities that are familiar. Yeah, so Satar asked about trying to select P in a way to minimize the right-hand side. P is not allowed to depend on S, which is the sample. There is work trying to look at priors that depend on so P can't depend on a particular sample S, but it can depend on the distribution of S. And so if you were to know that distribution, you could choose maybe a prior in a clever way to minimize things in expectation. There's also work on data-dependent priors, which do allow P to depend on the particular sample S. So yes, ideally you would select P to minimize the right-hand side, but you're not allowed to directly minimize it with respect to P in a way that depends on the particular sample S. Satar, let me know if that didn't answer your question. Okay, so the other question is there an intermediate step between the expectation and the soup, taking the soup over the hypothesis class first? Oh, that was not what I meant to do. Sorry. Taking a soup over the hypothesis class. Yeah, so each hypothesis is going to give you, where is it? Here, some true some true risk of that given hypothesis, right? So this is basically replacing an integral with an upper bound on, like, this is basically applying like a term-wise upper bound to the sum, I believe. Let's see. Yeah, great. Okay. Do we know how KLQP? Okay, there is work on how KLQP scales with n, I believe. We don't go into that. So we kind of focused on PAC Bayes bounds, which can be kind of directly computed. There's quite a bit of work on PAC Bayes bounds, which give you asymptotics for how things converge. That would maybe have more insight into how KL QP scales with n, but I'm just less familiar with that literature. Yeah, Andrew, do you know kind of how it would tend to scale?
I don't have a particular paper in mind for this right now. I'm sure there's work on it, but I don't have anything in mind. Sorry.
Yeah. Or an arbitrary. How do we interpret the expected loss over an arbitrarily selected distribution? So you can sample from the distribution, I guess. Right on like so final bound, upper bounds, I guess these two expectations under Q, and you could sample a lot of times and compute, I guess, this, and then that would give you some sense of how big it is. Yeah. Oh, that's for question of choosing P optimally. Yeah, I think maybe you can use, Andrew, is it right that you can use Hofting again to remove if you take many samples from Q on the right hand side?
What are you trying to remove? Sorry.
So Satar asks about how do we interpret expected loss over an arbitrarily selected distribution?
Yeah.
Yeah. Okay.
I guess it is as defined. Is that maybe the definition was unclear, or is there some different question being asked?
Can I try to clear the question?
Yeah, sure. Go ahead.
So my question is, what does it mean for the practical application? So we basically select a quite arbitrary distribution P for the prior, and that gives us an arbitrary posterior. Because in the PAC theorem that was presented earlier, so the meaning is quite clear to me. That means if our hypothesis space is discrete and this is the size of the space, we have this theoretical bound on the risk. But here we're selecting quite like user-specified distribution P, and we get this theorem that gives us an upper bound in terms of P, but what does it mean in practice?
This one may be part of a confusion. This 1 minus delta is with respect to draws from a data generating distribution. So left and right hand side are both random, and they are random because S is random. This 1 minus delta isn't related to Q or P. Does that clarify, or is it still, or is there a different question you're asking?
No, definitely. That helps certainly with the statement. But we're still kind of averaging over Q.
Yeah.
Okay, that's fine.
Yeah, it's a bit funny, but yes, yeah. Okay, so the other thing I was just going to briefly mention that we've already gotten to in part is that there's generalizations of this bound that allow the prior to depend in certain ways on the data set. And this is an older work on that, but there's also more recent work. I think Andrew linked one in the chat. And there's also people have given bounds that kind of relax this IID assumption and replace it with something weaker. Okay, so Javier is going to get into some applications of PAC Bayes, and so I'll hand it over to him.
Cool, thanks. I think there might be one more question in the chat, which you can answer if you want before I get going.
Yeah, so the question was, what's the motivation of Q and P driven bounds? Is it to handle hypotheses classes that are not finite? Because you could do that with random macro complexity or VC bounds. Yeah. So a motivation is definitely to handle hypotheses classes that are not finite. There are also cases where these PAC Bayes bounds are non-trivial, but bounds based on VC or random macro complexity would be or non-vacuous. And so Javier will actually hopefully give some motivation in terms of that when he discusses applications.
Cool, thanks, David. So I'm going to share screen, and you guys let me know if it works. So can you see a slide?
Yeah, that works, and we can see your mouse.
Oh, fantastic. All right. So I'm going to discuss the application of some of the stuff that Andrew and David have talked about to the neural network setting. And I'm going to cover a bit of material more at a high level than David and Andrew. So I would say if anything is unclear because I gloss over some detail, then I would encourage people to just unmute themselves and ask a question or put it in the chat. So let's get started, because I want to, there's various aspects that are interesting that you can do with these results. Let's get started. So as some motivation, there's this paper that Andrew mentioned at the beginning of the talk called Does Understanding Deep Learning Require Rethinking Generalization? And the authors show that when you train a neural network with SGD, you find solutions that have two interesting characteristics. The first is that while they obtain zero training error, so this is a zero empirical risk, they can still generalize quite well. So their generalization risk is also low. They do not overfit. And also, we're able to train these models when the labels are randomized. So we're able to train these models on garbage data and still obtain zero training error, so zero empirical risk. And of course, when we do this, our generalization risk is very large. Our model does as good as random guessing. So neural networks can overfit quite easily, but don't in practice. And why? So perhaps PAC Bayes thinking can help us understand this, but it's not quite so simple. So let's sort of naively take some of the ideas that Andrew spoke about and try to apply them to a neural network. And so let's consider a simple neural network with a single input dimension, a single output dimension, 2 hidden layers, and 100 hidden units, and no biases. So this is a very small model, but it already has over 10,000 parameters. So if we choose a naive hypothesis class, which in which we consider every setting of the float 32 weights of the neural network. So the size of our hypothesis class is going to be that number there. And we try to apply this finite hypothesis space bound, which Andrew derived applying a union bound to the validation bound. And we choose, say, a failure rate of 0.2. We immediately see that we need a number of points that's greater than 100,000 for the right-hand side of the bound for the looseness term to be less than 1. And often these very small models are very successful when trained on much smaller data sets. And if we sort of take this idea to ResNet 50, which is a very common image classification model that has 23 million parameters, we find that we would need to train our model on the order of 255 million data points in order for our bound looseness to be less than 1. So in practice, again, these models work very well, despite being trained on much smaller data sets. And analogously, if we were to take a PAC Bayes bound, like the ones that David talked about, and we were to define our prior uniformly over every possible function that the network could express up to float 32 precision, we would obtain vacuous results. And when people say that results are vacuous, what they mean is that the generalization error is bounded by a value greater than 1. So that's saying something along the lines of the error probability of this model is bounded by over 100%. So it's not very useful. So, and actually, before I move on, with regards to the question on VC dimension or other types of bounds, those are often not very useful here either, because the VC dimension of a neural network, so we can't compute it exactly, but we can put some upper bounds on it, and all of our bounds grow quicker than the number of parameters grows. So this results in approaches that use this VC dimension to also end up being vacuous, to the best of my knowledge. All right, so can we do better? So we can make a couple observations. For the first is that neural networks are relatively insensitive to noise in their weights, and we can even quantize these weights to reduce their precision from float 32 to even 8-bit with negligible loss in performance of the network. And we can even remove large sets of weights of the neural network. We can perform pruning. And there are results that have shown that you can prune over 99% of a network's weights and still do very well in terms of accuracy. So perhaps the complexity of the functions found by fitting neural networks is much lower than the number of parameters would suggest. And this is what we're going to discuss next, how we can exploit this idea to find non-vacuous bounds. Cool. So let's fix some failure probability delta and some prior on our hypothesis space and collect some data set from our data generating process team. Something that we could do is try to optimize our, what I'm going to call our posterior distribution Q, our distribution over models, using the bound that David presented, which is going to look like this. And if we're going to do this, there's a couple of computational considerations. First of all, this 0-1 loss is non-differentiable. So in practice, something that one could do is use a convex surrogate upper bound to this loss, which I'm just going to call little RSQ hat. And it's simply the logistic loss. The choice of Q can be very simple. It can be a multivariate diagonal Gaussian over the weights of the neural network. If you're familiar with Bayesian methods for neural networks, this is the default choice in that setting as well, or one of the most common ones at least. And finally, the choice of prior is of course difficult. It's difficult to reason about what would be a good prior in this setting. In this specific paper that I'm referring to here, the choice is a isotropic Gaussian distribution, and a very important parameter is the variance of this Gaussian. And what the authors do is, instead of specifying a single variance parameter, they specify a set of variance parameters and loosen their bound using a union bound argument, similar to the one that Andrew explained before. So then they're able to sort of choose the lambda from a set, and they end up taking the one that works best for them. So to put this into a concrete algorithm, we can, this is what the authors do. They fit a regular neural network using SGD until convergence. They then initialize the parameters of their distribution Q. They set the mean to the local optima of the loss found by SGD, and they initialize the standard deviation to be the magnitude of the weights. And then they optimize the bound until convergence, noting that the empirical risk term is upper bounded by a differentiable convex surrogate. Cool. And once optimization is complete, they say we're going to estimate the original bound using the original empirical risk term and samples from our approximate distribution Q. So some intuition for why doing this might be a good idea. Local optima that live in flat regions of a neural network loss surface have a smaller description length. This is a decently well-studied phenomenon, and we might think that this is one intuition for reducing the inherent dimensionality of our model. And another one, coming from a more Bayesian perspective, is that what we're doing is very similar to optimizing a variational lower bound on the marginal likelihood, which is what's done by this method called Bayes by backprop, which also places diagonal Gaussian distributions over the weights of neural networks. Probably, if you're familiar with variational inference, you've made this observation already, but the objective that we're optimizing looks exactly like a expected log likelihood. That would be the left-hand side term here, and a KL divergence, which is the two parts that constitute the alpha, with the exception that the KL divergence is contained, in this case, within a square root. Cool, so let's look at the results. So this table which the authors provide, contains a bit of information, but there's a couple of parts that are specifically interesting, and I'll walk you through them. So they fit two types of models, some with true labels of the MNIST data set, and others with the randomized labels. And on the first row, the models that have a T correspond to true labels, and the ones with the R correspond to random labels. So the second horizontal row is the training error, which all models converge to a very low training error, despite having random labels or not. And the third row is the test error. And all models that are fitted with true labels have low test error, and the model that's fit with random labels has a test error of close to 0.5, so it's doing about the same as random guessing. This is because this is a binary MNIST task, I believe. But if we look at the fourth row, the PAC Bayes bound, we see that for all of our models fit with true labels, the error is bounded by, the generalization is bounded by numbers, in the region of 0.17 to 0.23, which is reasonable. This is a non-vacuous bound. It's not tight by any means to the true test error, but it's notably less than 1. And when our models fit on random labels, our PAC bound gives us a value of 1.3. So this is quite helpful because we're finding bounds that are not tight but non-vacuous, and this bound can warn us if our model will not generalize. And if you want to get some intuition for why this worked, the next row to look at would be the KL divergence between the distribution Q that was optimized in the prior. And for all of the models that use true labels, it's much smaller than for the random labeled model. And I guess what this tells us is that the random labeled model found a much narrower or much smaller region of the loss surface than the model trained with true labels. All right, does anybody have any questions at this point about why this worked, what's going on here? Cool, otherwise I'll move on. So this was a very interesting paper because I think it was the first to obtain non-vacuous bounds for neural networks. But of course it's on MNIST with relatively small networks. And there has been some subsequent work that scales this to larger models on the ImageNet dataset, which is much larger. And I'm not going to go into a lot of detail, but I will say that this method is based on a key observation, which is that the KL divergence can be seen as the expected number of bits needed to encode a message sampled from our distribution Q when using a coding scheme optimal for some other distribution P. And using this, we can, or the authors of this other paper are able to derive bounds for very large networks once these networks have been first pruned and then quantized. So many weights have been set to 0, and the rest have been, the precision of the remaining weights has been reduced. Specifically, they obtain a bound of 96.5% when the validation error is of 35%. So of course, it's very loose, but somewhat impressive because it's non-vacuous for very large models. Cool. So that ends the application of these bounds to neural networks. And now I'm going to talk a little bit about the connection between PAC Bayes and Bayesian inference. But to do that, we're going to have to define some new objects. First of all, Bayesians often don't care about the log loss, the expected risk as described before. As David mentioned, they're often a bit more interested in an object that looks like this, where we have some model, some likelihood function, which we'll call P of y given x, comma h, and we are going to integrate out our hypotheses by taking an expectation over the posterior distribution Q. And ultimately, what we care about is the log loss associated with our model when our hypotheses are integrated out. And we're going to call this from now on the cross entropy loss of Q. So you can think of this as a generalization loss, but with our with H integrated out over our posterior Q. And before, another key idea is that we worked with losses that were in 0, 1, and often likelihood functions are like that. So we need to switch to working with log loss functions that look like this. So that are log likelihoods. So now we're going to call our generalization risk. It's going to be a minus log likelihood. And when the data is sampled from the true generative process of the data, and our empirical risk is going to be the minus log likelihood of some hypothesis when the data is coming from our data set. Cool. And a key idea is that using Jensen's inequality, we can see that our cross entropy loss is going to be upper bounded by our generalization loss. So the term that PAC Bayes seeks to minimize is an upper bound on the cross entropy loss, which is what Bayesians often care about. Cool. So the first issue that we're going to have is that the bounds presented so far don't really consider these log loss functions, these log likelihoods. But there are many types of PAC Bayesian bounds, and fortunately there exists some that do admit these forms of risk functions. So we're going to consider this one specifically, which is very similar to the ones mentioned previously in this talk, but notably the square root is gone. And this is interesting for many reasons, but I think the most, for the purposes of this talk, is that if we consider that delta, so our failure probability, and this psi term, if we realize that they're constant with respect to Q, and by the way, this psi term is just this log of an expectation over our prior and our data distribution, which also appeared in David's derivation. If we consider that these terms are constant with respect to Q, and we fix C, which is another constant, to 1, and C is a constant that we choose, the right-hand side of this expression reduces to the alpha. I think I saw a question in the chat, but I can't actually see the chat. I just saw a little pop-up. If there is a question, can somebody read it to me, perhaps?
Yeah, Alberto asks, in order to obtain these non-vacuous bounds, you have to actually run training of the model, which is quite costly. Once you have trained the model, testing its generalization is relatively cheap. So what's the point of having bounds that are useful only provided that you train the model?
That's a good point. And I think that you're right in questioning the usefulness of that. I would say that that paper that I spoke about was interesting more because people were able to get, the authors were able to get these non-vacuous bounds. I don't think that it was presented as a practical tool, perhaps a step in the right direction. Cool. Let me see. Okay, cool. So right, we make this observation that this PAC Bayes bound corresponds to the elbow plus some constants that don't depend on our approximate distribution Q. So as we well know, this bound is going to be minimized when Q matches the Bayesian posterior. And so then if we're interested in minimizing our cross entropy error, it seems like the above bound could be a good idea. But I guess that what we need to question is if our generalization risk, RQ, also minimizes our cross entropy. So just before we continue to answer this question, let's take a quick aside to mention what model misspecification is. So we will say that our model is correctly specified if the true data generating process is contained within our hypothesis space H. So we can write this like this. There is some H, and given that H, our predictive distribution from our model will match that of the true data generating process. And if this is not true, then we say that we're learning under a model misspecification. All right, so going back to answering this question, is minimizing our risk, our generalization risk, also going to minimize our cross entropy loss? So it turns out that we know that the distribution that minimizes the empirical risk, sorry, the generalization risk, is a point mass at the maximum likelihood solution, under the assumption that we have observed an infinite amount of data, actually, which I should have probably put on this slide. But if we observe an infinite amount of data, then the maximum likelihood solution that we find, the optima of big RQ, will be a delta function at that point. However, we can see that this is only going to be a minimizer of our cross entropy loss if the cross entropy of this maximum likelihood solution of H fixed to the maximum likelihood solution is smaller than or equal to the cross entropy obtained by any model combination. So by any model where H is sampled from a different Q. So in other words, there must be a single hypothesis that's better than any model combination. Cool. So this just restates that point. And the first result I'm going to talk about is that of Masagosa this past NeurIPS, who shows that this is only going to happen under perfect model specification. In other words, the single best hypothesis is only going to be better than any model combination if our model is correctly specified. And in other words, if our model is correctly specified, this means that the KL divergence between our data generating distribution or our conditional data generating distribution and the distribution implied by our model when the hypothesis is the maximum likelihood is 0. Which is the same thing as saying that the entropy of our data generating distribution matches the cross entropy when we fix Q to the maximum likelihood solution. Cool. So what happens if our model is not correctly specified? Then it follows that Bayesian inference will not be the optimal thing to do. And let's see if we can do any better. And so what this author proposes is to sharpen our previous bound. So this bound stated at the top of the slide, which is just Jensen bound, using a second order Jensen bound. And that's going to look like this. So we have that our cross entropy loss is going to be bounded by our generalization risk minus a new term called VQ. VQ is always going to be positive. So we know that this is also going to be in turn bounded by our generalization loss alone. So VQ is a variance encouraging term. And it looks like this. So it's just the expectation when we sample our data from our data generating distribution over 1 over some constant that's not interesting to us, times the expectation from our posterior Q of the predictions or the density assigned to labels by our model given the hypotheses that are sampled, minus this other term, which is the predictions made when we marginalize H. So you can think of this as a marginal distribution. So what this is telling us is that this term is going to take positive values when the posterior is different than a delta function. And when the posterior matches a delta function, then taking this expectation is just going to put H maximum likelihood in here, and both of these objects will be equivalent. So VQ will become 0 otherwise. And this is going to happen, or this is going to be optimal in the case of perfect model specification. So if we have perfect model specification, VQ will go to 0. Cool. So this suggests that we can add this term to our PAC Bayes bound to get a tighter bound. And that would look like this. So we'd have that now our cross entropy is bounded by the generalization risk minus VQ, and which is bounded by the PAC Bayes bound from before, where we simply added this new term. So now let's look at some results, how this, what this does in practice. And to do that, I'm going to show a plot for the paper. But before showing the plot, because there's a lot on the plot, I'm going to describe it. It's going to be a scenario where we're considering a mixture of two models. And we're going to be doing inference over some parameter, which is called rho in the plot. And we can either choose, so rho is on the x-axis here. So when rho is set to 0, we're choosing the first model. When rho is set to 1, we're choosing the second model. And when rho takes some value in between, we're considering a mixture of the two hypotheses. First, let's look at the figure on the left, which is the case of model misspecification. Here we have that the second hypothesis is a bit better than the first one. We plot three things. The cross entropy loss, which sort of tells us that the optimal thing to do is choose a rho that's neither 0 or 1. It's to choose a mixture model. Then we plot the expected log loss. So this is going to be RQ for us, big RQ. And we see that it decreases monotonically and is optimized by choosing the second model. And finally, we see that the second order Jensen bound, so this bound up here, is actually tighter than the expected log loss and leads us to choose a model combination instead of a single model. Cool. And then under perfect model specification, which is the plot on the right, we see that the minima of all three quantities, or all three functions, are minimized by the single best model. So to summarize a takeaway from this, if we were to do Bayesian inference here in the model misspecification setting, and we were to observe an infinite amount of data, we would end up converging to, if our model is misspecified, we would end up converging to the to the second hypothesis. Well, that's actually not the best thing that we can do in terms of cross entropy loss. Cool. And finally, we're going to look at applying this to a specific toy problem. So again, there are many things on this plot, but I'm going to go through them one by one. So this is a regression setting where we're just fitting the slope and the bias of this regression line to some data, which are these blue dots. And crucially, we have misspecified the variance of the likelihood function. So we've underestimated the noise. So if we perform Bayesian inference, we will get something like this third plot where my cursor is. And because we have a lot of data, our uncertainty over our parameters does not really induce much uncertainty in function space. And all the uncertainty that we have is these orange bars, which correspond to the noise of our likelihood function. But again, this noise is less than the true noise of the data. And here in the first plot is the Bayesian posterior, and we see that over both theta 0 and theta 1, which are the parameters of our model, it has contracted a lot. It's a very tight distribution. When we apply this second order PAC bound from the previous slide, we get a result like is in this last plot here, in the one that's most to the right. And here we see that the parameters, some uncertainty has been induced in the parameters, and that's translating into function space. And that's causing increased uncertainty that matches the standard deviation of the data more closely, perhaps. And specifically, if we look at the posterior over parameters induced by this learning algorithm, we can see that theta 1, which actually corresponds to the bias, sorry, theta 0, which actually corresponds to the bias, has very large variance. So what's happened here is that the PAC Bayesian learning algorithm has decided to blow up the uncertainty in the bias to compensate for the misspecified model. So that's cool. However, something that I would question before wrapping up is the general applicability of this algorithm. So this, going back a slide quickly, or actually going back to this variance term, we are going to have to empirically estimate at the training data, which is what's done by the author of this paper. And that means that it's only going to encourage disagreement among our marginal predictive distribution and our predictives with hypotheses sampled from Q. It's only going to encourage disagreement among those models at the training data. And that works very well here because our model is misspecified in a way that underestimates the variance at the training data. However, if we're looking for other things, like often Bayesians look for increased uncertainty outside of the data distribution, outside of the region where the training data is, then I don't see how this algorithm would give us gains in that sense. So perhaps I would be cautious to say that that this learning algorithm solves many of the problems of Bayesian inference. I don't think that we can simply misspecify our model in any way and fix it with this learning algorithm. But yeah, that wraps up this section of the talk.
Maybe has a question, Javier.
Okay, yeah.
Vivian says, how hard is the derivation of the second order Jensens? Could you sketch it at the end, or is it quite involved?
So actually, I do not know. I don't know the derivation by heart. If you want to look into that, there is a paper called Sharpening Jensen's Bounds, and I skimmed over it in preparation for this talk. It didn't seem extremely involved, but I don't know. I couldn't sketch it right now.
There are a couple more questions. So Christopher Jensen says, did the authors or any subsequent papers compare these two bounds on non-toy data?
Yeah, so that's a very good question. So the author of this paper, Andres Masegosa, has some experiments with some large-scale image classification networks. My impression from those experiments is that you get gains sometimes, but they are not humongous. Potentially, that has to do with the fact that you need to specify, well, that he specifies a Gaussian posterior Gaussian Q over the weights. And that is perhaps a restrictive assumption to make for neural networks. And perhaps that's why he does not get a lot of gains. I also spoke to him in person a while ago and asked him about that, and he told me that it was difficult to see gains in these very large, very flexible models using this learning technique.
There's a more the general question from Alexandru Chiova. I'm sorry if I mispronounce your name. Do you want to maybe unmute yourself and ask the question because it's reasonably long?
Yeah, sure. Sorry about that. So yeah, just a question to kind of help my understanding sort of coming to this from a different perspective. So the usefulness that I imagined initially for these probably approximately correct bounds on generalization come from computational learning theory, where these bounds are used to basically make statements about certain problems that admit efficient algorithms in epsilon and delta that achieve a certain generalization. And these bounds in terms of VC dimension usually come into these problems, right? So efficiency is important because, for example, if I mean, you can always kind of home in on a good hypothesis by just random sampling, except that usually this process is exponential in epsilon and delta. So there are these toy problems for which people solve this computational learning problem by just saying, okay, we have a good selection rule for H in terms of S for this hypothesis. Right? Just curious if there's anything similar in the PAC Bayesian setting. So is there any statement on the efficiency of being able to learn Q of S that achieves a certain generalization bound?
Okay, so I'm not an expert on the. Actually, I'm very unfamiliar with the computational efficiency analysis. I did read a like a machine learning PAC textbook introduction, and they said that often what they do is they take the probably approximately correct part from PAC and they ignore the computational part and they focus purely on things. And most of the PAC-based papers that I'm familiar with have not really thought about trying to prove that computationally you can achieve a certain predictor with a certain generalization with a certain computational complexity. They've usually mainly been concerned with statistically what kind of generalization guarantees you can obtain and what rates you need to obtain those guarantees in terms of how fast your data is growing and stuff like that. But I'm not super familiar, so there might be also literature that talks about computational complexity, but I'm not aware of it. David, Javier, have you heard of?
No, as you said, I've definitely seen papers that talk about statistical efficiency, but less sure about computational efficiency.
So I think that to further clarify, it's still so it's still statistical in the sense that there is you know, for example, if you think that your algorithm or your selection rule is stochastic gradient descent, right? There's still a problem in kind of statistically obtaining bounds for the efficiency of Q of S. It's just that if you allow yourself to, so these bounds apply to any Q and any P, right? But if you allow yourself to narrow down Q of S by just saying, okay, this is the result of this particular algorithm, right? Maybe maybe there is a result that says, okay, for this type of problem, this type of algorithm achieves this kind of bound, and also this algorithm is, you know, I mean, the computational efficiency bit is just to kind of rule out very stupid algorithms that just randomly sample from your hypothesis class and by the end of time achieve some good generalization bound. Home in on a hypothesis with generalization.
Yeah, can you actually clarify that a bit? So if you were to do this random sampling that you're suggesting,
yes,
to actually home in on a hypothesis, you would need a lot of like the variable that, or the constant that we've denoted by n would have to be quite large, right? In general.
Well, so you're interested in achieving a certain generalization bound, right? And you have you're able to compute the empirical risk, right? And you know that the empirical risk is for any hypothesis within, let's say, some small gap of the actual risk, right? So then if you can, this is the PAC bound.
But you know that that risk has to be independent of the data set unless you're going to use a union bound, right? So you can't look at the empirical risk to choose your hypothesis in that setup, right?
So I think the whole point of this is that if you, so as you said, if you use the union bound, right, you can use your empirical risk. If you use the VC dimension kind of classical bound, then again you can use the empirical risk, and the gap is now in terms of your VC dimension. So whatever formulation of the gap makes sense.
Okay.
But yeah, in general, what I was trying to say is that this kind of computational efficiency bit is not the crux of the statement. Most of the algorithms that we produce are in some sort of way computationally efficient. What they don't do is they don't give you guarantees on generalization. But yeah, you need to make the statement in order to kind of rule out stupid algorithms that just randomly sample until you hit a good enough hypothesis. So my question was more along the lines of, have we been able to say, well, here is a selection rule for Q in terms of S that achieves some good generalization? I mean, I'm sure that once you give me a selection rule, the selection rule will be, polynomial and epsilon and delta or something like that, because it's very hard to get something else. But are there any problems that are shown to be solved by?
This might be a slightly indirect answer, but it's common to consider the generalization guarantees you get from Gibbs posteriors,
right?
For which I don't think we have an efficient way of sampling from them, because you'd have to run Markov chain Monte Carlo most of the time, and I don't think there's provably efficient ways of sampling from them. But it's also common to just consider the generalization bounds you get from those. I'm not sure if that's related to what you were saying.
Perhaps. I'm not sure. I was just curious if you have any kind of literature in mind that would point to basically
I'm sorry, I think
selection problem.
I think that might be beyond me in terms of what I know about the thing. Then it might be there, but I just might not be aware of it. There's a huge sections of PAC Bayes literature that I'm not aware of, so it's very possible that I'm unaware of the relevant literature.
That's okay. Thank you. It was a great talk, by the way.
Thank you.
So we're going to stop the recording now, although you're welcome to continue the discussion. I think we have at least one more question in the chat. Thanks so much, guys, for the great presentation. It was really enjoyable.